Let's define three different planar coordinate systems that will come in handy in this class. So the first will be Cartesian coordinates, which hopefully you're familiar with by now. That's what we've used so far. And then we'll introduce two new ones, polar coordinates and path coordinates. We'll use the trajectory of particle P along this path to demonstrate each of these coordinate systems. The first thing that we need in any description or problem is a reference frame. And so here we see the reference frame I that's defined with three basis vectors, E1, E2, and E3. E1 pointed to the right, E2 up, and E3 out of the page, and it has an origin of O. Let's work with the position vector from O to P, so R of P with respect to O. And if we define this in terms of our Cartesian coordinates, then we'll have a coordinate from the origin along E1 that we'll call X, and a coordinate along E2 from the origin that goes to point P that we call Y. And so the position vector RP with respect to O is the magnitude X, or the coordinate X, in the E1 direction plus the coordinate Y in the E2 direction. And another way to say this is that our position vector from P with respect to O, seen in the inertial reference frame, according to this inertial basis, is defined by the coordinates X and Y. Now even in this basis, with E1, E2, and E3, we're not constrained to using a single coordinate system. We're not constrained to Cartesian coordinates. So let's define another set of coordinates that's based on an angle theta and then a telescoping length r. Now using these coordinates, r and theta, we still need to relate these to the directions of the bases, E1 and E2 in this case. So let's take a look at our position vector and define it in terms of r and theta. So r of P with respect to O is going to be equal to, instead of x, we can replace this with r cosine theta, that'll be in the E1 direction, plus r sine theta in the E2 direction. And what's important to see here is that we've taken this 2 degree of freedom system, and we know that with 2 degrees of freedom we need two coordinates. We started out with Cartesian coordinates because it's intuitive to us, in which we know that this particle P can move horizontally or vertically, and we've defined those distances. And now we've replaced with two other coordinates so that we don't need x and y anymore, but instead we can define everything based on r and theta. And so the path of this particle P will be dependent upon the length r and then the theta that's with respect to the basis E1. Now this brings us to path coordinates. And path coordinate is a completely different animal than either Cartesian or polar coordinates because there's only one coordinate. Now, quick review on Cartesian and polar coordinates is that we're using two coordinates to describe the planar motion in which this particle can move in any direction. This just happens to be the path that we're following right now. Now, with a path coordinate, we do add one constraint, so we can only use a single coordinate. And the constraint is that we know what this path is, and we can define that mathematically. And so with that knowledge in hand, if we can define the path mathematically, then we can pick any point on the path to be the origin of the coordinate system, and then we're defining a coordinate S along the path that defines, so it's a scalar length S, and if we know the length, then we know the position of particle P anywhere on that path. So you're probably already seeing or recognizing the problems with using path coordinates to define a position. We have to have a really well-defined mathematical function, and then to relate this back to a position vector, as I've drawn here, we really need to convert that back to some other coordinate system, to a Cartesian coordinate or to a polar coordinate, to be able to obtain that vector. So we typically don't use path coordinates a lot for position. However, where path coordinates will come in incredibly useful will be in defining instantaneous velocities and instantaneous accelerations, knowing the instantaneous curvature of a path. And that'll become more clear as we begin to use these. Let's apply these three coordinate systems to a normal or a non-inverted simple pendulum system. So first, let's draw our reference frame. And so here we have an inertial reference frame that has an origin of point O and the basis vectors E1, E2, and E3, where E3 is along gravity, E3 is pointing out of the page, and then E2 will be the cross product between E3 and E1. So now let's define the location of the pendulum in Cartesian coordinates, which means that we need to have an x and a y. We'll define positive x to the right. We'll define positive y down. And so our position vector of point P is equal to y in the E1 plus x in the E2 direction. So what you should notice here is that we didn't automatically write down x in the E1 direction, y in the E2 direction. And that's because we've defined our basis vectors here, E2 pointing to the right and E1 pointing down, and our coordinate y is going to correspond with E1, our coordinate x will correspond with positive E2. And then the next thing that we notice about this system is that although we've defined two coordinates, an x and a y, the motion of this system is a pendulum motion, and so x and y are connected to each other. So this is a 1 degree of freedom system. We have two coordinates, and we need to connect those two coordinates. And we do that using a constraint equation, one that we've used before, which is x squared plus y squared is equal to L squared. Now let's turn our attention to polar coordinates. And for these coordinates, we'll define an r and a theta, r being the distance between the origin and point P, and then theta being the angle between the basis vector E1 and the line OP. And so our position vector, r of P with respect to O, in the E1 direction, this direction is defined, or that magnitude is defined as r cosine theta. And then in the E2 direction is r sine theta. And just like with Cartesian coordinates, we need to apply a constraint equation. So the constraint equation that we used earlier, x squared plus y squared is equal to L squared, is the constraint equation only for our Cartesian coordinates. Now with polar coordinates, we have a new constraint. And so the constraint here is conceptually and qualitatively the same, which is that the distance between O and P will always be the same, even though that P is moving. And so our constraint, when we write this, is that R is equal to L. And now you can see that with polar coordinates, when we apply this constraint, the appropriate constraint to make this and to recognize that this is a 1 degree of freedom system, the entire motion of the pendulum itself can now be described by a single coordinate theta, which is intuitive to us. When we look at something rotating like a simple pendulum, we tend to think in terms of theta or an angular speed. So now let's define the motion of the pendulum in terms of the path coordinates. Now recall that we said to be able to use a path coordinate, we have to have a well-defined trajectory. And for a simple pendulum like this, the trajectory of particle P is creating a circle of fixed length around the origin. So that allows us to define a starting point, and then the distance s would be the arc length as the particle P travels around the origin in that well-defined path. So for our path coordinate, we're not going to write a position vector, but we'll write a coordinate that simply s is equal to L, because the radius of that path doesn't change, L multiplied times theta, that would give us the arc length. And you see here that with a path coordinate, we've had to define this path coordinate in terms of some other coordinate. So it's not completely internally independent. So we've had to define it as L theta. We could also manipulate this so that S is defined in terms of an X and Y or Cartesian coordinates. One last thing to point out is that we've applied each of these coordinate systems, Cartesian, polar, and path, to a single reference frame, in this case the inertial reference frame. And so we can convert between these coordinate systems, as you've been able to see, between the xy, between the r thetas, and then connecting the path coordinate to each of those other coordinates. In the future, we'll take advantage of the polar coordinates and path coordinates and use those to develop new reference frames that accommodate those coordinates really well and even give you more intuition about the systems. But for now, we'll always use these coordinates within an inertial reference frame, understand how to convert between the coordinates when needed, and then start developing your intuition about which coordinates are going to be best for each individual problem that we solve.